in that part, I will talk about types of machine learning. So I will start with what are the types of machine learning models. So also we will go into details later on. So don't worry if there are something which, but if you have any questions, just ask your questions, please. So, okay. So we need to talk about types of machine learning. So we talked last time about supervised learning and unsupervised learning. So first we will start with supervised learning. So this is by far the most common case. Most of machine learning models which are developed around us, it's for supervised learning, not for unsupervised learning. So this is very famous and a very common technique, which is supervised learning. And it consists of learning to map input data to known targets. So it's very important to have known targets. So similar to the IRIS dataset, in IRIS dataset we have 4 input features. I will just call it A, B, C, and D, for example, A, B, C, and D. And we have here one column called labels or targets. So we try to map inputs into the target. So if you have the target signal with you, it means that this one is supervised learning. So you have some examples. So this is different species, for example, and each species will be classified into one class. So if you have the target feature, it means this one will be supervised learning. And it is used for classification and regression. I mean, this technique is used for classification and for regression problem. So we can use it for classifying some examples into some target classes, for example, or labels, or we can use it for regression. One example for regression, for example, you are a software engineer, for example, you have some years of experience, you have different, educations and training, for example, so how much salary you should get, for example, next year or from your current job. So this is a kind of regression problems. In case of unsupervised learning, this branch of machine learning consists of finding interesting transformations of input data without the help of any targets. We don't have any targets. So when it is unsupervised learning, we don't have this target signal. And it is used for data visualization, data compression, data denoising, or to better understand the correlations which exist in your data at hand, for example. And supervised learning is the bread and butter of data analytics. It's a very important branch. Why it's important? Because most of the data around us is unsupervised. Most of the data around us does not have labels, does not have any target. And it is often necessary step to better understand a data set. If you have a data set, you want to understand it, you want to visualize it. So it's very important to try to apply some unsupervised technique to understand your data, to visualize your data first. And after that, you can select the model which will be used for classifying it, for example. So one of the famous techniques, in fact, it's dimensionality reduction. We can use a dimensionality reduction to reduce the dimension of your data set. So imagine that in IRIS dataset, we have A, B, C, and D. So we have 4 features. It's difficult to visualize it, for example. So if I need to visualize it, maybe I will plot A, B, and Y together, or maybe I will plot A, C, and Y. So it will be difficult to visualize all information. So one way for solving this problem is to use dimensionality reduction. So I can use those 4 inputs as an input to a dimensionality reduction algorithm, and the output will be the principal component. I can select the first 2 principal components to visualize my data. So I can use the dimensionality reduction technique, which is unsupervised technique, to try to lower the dimension of your data. So it can help you to visualize your data in a better way. We can use it for clustering into some categories, for example. For example, here in this classification problem, we classify this problem into one of the 3 classes. If it is IRIS dataset, we have 3 classes: IRIS, Setosa, Versicolor, Virginica, for example. So I can use a supervised technique to classify my examples into one of those 3 classes. But in case of clustering, in fact, maybe in this clustering problem, we don't know the categories. We don't know all the categories, for example. So maybe one day I will cluster it into 3 clusters. Maybe in the next day I will get a new cluster. So we need to cluster it into 4 or 5. So you have more freedom when it is unsupervised learning problem. you will have more freedom in your problem. And in fact, in supervised learning, AI models which are used in supervised learning, we call it weak AI. Why it's weak AI? Because this supervised learning problem, it's well-defined, the problem, because I have inputs and I have target features. But in case of unsupervised learning, we call it strong AI. Why it's a strong AI? Because the problem is not well-defined. Because I have only input features, I don't have a target feature. So the AI model, which we will get from unsupervised learning problem, we call it a strong AI. But the AI model which we are obtained from the supervised learning, we will call it weak AI. So we have weak AI and we have strong AI. Also, there is another technique which called self-supervised learning. Self-supervised learning, and the self-supervised learning is supervised learning without human annotated labels. So self-supervised learning is supervised learning but without human annotated labels. You can think of it as a supervised learning without any humans in the loop, for example. So there are still some labels involved, but they are generated from the input data. We have some labels, but we will obtain those labels from the generated data using some heuristic algorithm. So we need to use a heuristic algorithm, and this heuristic algorithm will generate labels from my data. So for example, predicting the next frame in a video, for example, given past frames, or the next word in a text given previous words. So we call it self-supervised learning. At the end, also, we have very important branch of machine learning, which is called reinforcement learning. Reinforcement learning is very important, and it is more about robotics and practical uses of maybe autonomous cars, autonomous vehicles, and so on. In reinforcement learning, we have an agent. We need to develop an agent. We call it intelligent agent, for example, and this agent will receive information about its environment. So this agent, just imagine that this agent is a robot, and this robot will be connected with some sensors, and those sensors will try to sense the environment, and it will try to, and it have a set of actions, for example, and it needs to select an action which will maximize some reward. So, for example, you have a robot, and you are at point A in a room, for example, and I need to go out from this room to the corridor to another room, for example. So I need to go from A to B, for example, right? So it's a very complex task, in fact, for a robot, because I need to navigate, I need to go out from this room, I need to select the right direction, I need to move into the corridor, and I need to enter the next room and go to that location number B. So it's a very difficult task. So in this case, we need to develop an intelligent agent. This intelligent agent will be connected with some sensors. Those sensors will try to sense the environment to avoid hitting walls and people and animals and so on. And it will have a set of actions. Those actions maybe go forward. For example, if you are here, maybe you will go forward, turn left, turn right. So you can have 3 actions. So maybe the optimum way is to maybe go out, go forward, and after that turn right, correct? Go forward until at that point here, turn left and go forward. So you have a set of actions. So in fact, this reinforcement learning algorithm, it will try to learn how to select the best set of actions to go from A to B, for example, in the shortest time, because I can go from A to B in 24 hours. So this is not good, in fact, policy. So the idea here is to go from A to B. Imagine that it's at hospital, for example, and my robot should deliver medications from room A to room B. Maybe room A is a kitchen, correct? And I need to deliver food, for example, breakfast. So I don't need to deliver this food maybe afternoon, correct? It should be as quick as possible. So in this case, we need to develop an intelligent agent, and this intelligent agent will try to sense the environment, and it will try to select actions which will help the robot to achieve its goal as quick as possible, to go from A to B, for example. So it will learn to choose actions that will maximize some reward function. So maybe this reward function is to go from A to B in the shortest distance. I need to minimize the distance, correct? Because in fact, I can go from A to B, I can go into the wrong direction, take a trip somewhere, and after that, I back here after 1 hour, correct? So in this case, in fact, I achieved my goal, but it takes too long time and I have been driving for longer distance, making a noise to other people, spill food, and so on. So in this case, maybe my reward function will be to minimize a cost function, and this cost function, maybe it will be the distance I need to reach from A to B using the shortest distance or shortest time, for example. So we can use a neural network which looks at a video game. Another application, for example, maybe we have a video game, for example, and we have some game actions which we need to select to maximize the score, for example. Maybe I can use a neural network which is connected with a camera, right? And it will try to select the actions which will maximize my score. So we can do this using reinforcement learning. Reinforcement learning, it requires, in fact, simulated environment or a game engine, because if you need to train a robot to go from A to B, a physical robot, maybe this robot will hit the wall several times, maybe it will destroy itself, maybe it will hit other people. So it will be much better to try to simulate this scenario in a game engine, correct, or a simulated environment, and try to train the robot in a simulated environment before implementing it in real time. Because also in simulation, it will be much faster. I need to go from A to B. You need to specify the speed of your robot. Distances should be realistic. And after that, he will try to train this agent in a simulated environment. And after being happy with the performance of your agent, you will just deploy it in your real world robot. And after that, you will test your robot in real world scenarios. So in supervised learning, we learn from data, correct? And in the reinforcement learning, we learn from mistakes, correct? So in supervised learning, we learn from data because we have this known targets, for example. So we try to learn from data. But in case of reinforcement learning, we will do some mistakes and we will try to learn from those mistakes to achieve our goal in the shortest time and using the shortest distance, for example. There are types of machine learning problems. For example, there is, binary classification problems. When it is binary classification problems, it's a supervised learning where the training set is labeled, for example, and the classification task where each input sample has only two classes or two options. So it could be yes or no, for example, or it could be 0 and 1. So for example, I have very simple problem like dogs and cats. So I have images, and on those images we have cats and dogs, and I need to build a machine learning which can classify a cat as a cat and a dog as a dog, for example. So in this case, it will be binary classification problem. It could be sentiment analysis, for example, sentiment analysis problems. For example, sentiment analysis, it's like I ask my customers to write a review about a movie, for example, and I want to see if those reviews are positive or negative, if people like the movie or not. So in this case, it's a binary classification problem. And in this case, maybe I can use a recurrent neural network to classify each review as a positive or negative. So at the end, we can say that if we have a movie and if 1,000 people they have been watching it, and if they wrote reviews about it, maybe if 60 people like it and 40 people don't like it. So in this case, we can just say that, okay, it's 6 out of 10. So people will look into this number as are people who want to watch movies, and if it is very low, maybe they will not watch it. So we can use this one for recommendation systems. So if this number goes high, for example, if it is 8.5 out of 10, it means it's a good movie, in fact, right? So we will get this score based on sentiment analysis of reviews of movies, for example, or a product. So and based on those numbers, we can build a recommendation system which can be used to recommend a movie to a people, for example. Usually, before watching a movie, for example, in Netflix, for example, people try to check those reviews, and if those numbers are high, it means it's a good movie. So you can just don't waste your time for watching a bad movie, for example. So medical diagnosis also. So if you have a patient in a hospital, and if you have some X-rays, for example, and if you need to detect if the patient has a kind of disease, maybe we can just maybe this problem will be binary classification problem if he has the disease or if he does not have such disease. Spam detection, for example, when you are getting some emails, spam. So it's also binary classification problem. If it is a spam, it will go to the spam folder, correct? If it is ham, it will go to your normal So you will be able to read it, for example. So it's binary classification problem also. We have different types of classification problems, which is multi-class classification. So in binary classification problem, we have two classes. If you have more than classes, we will call it multi-class classification problems. So in multi-class classification problem, it's a classification task where each input sample should be categorized into more than two categories or classes. Maybe it could be three, similar to IRIS dataset. So if we can, IRIS dataset, if you still remember it. So in IRIS dataset, we have three classes. So it's a multi-class classification, right? IRIS dataset is multi-class classification. Handwritten digits, for example, MNIST. There is famous dataset called MNIST. So it's also, we try to classify each image into one of 10 classes from 0, 1, 2, until 9. So this problem also, it's a multi-class classification problem. So if we need some examples, classify a set of images of fruits, which may be orange, apple, and the pears, for example. So in this case, it's a multi-class classification problem. Classify handwritten digits. This one, it's multi-class classification because we need to classify each image into one of those 10 classes. So we have multi-class classification. We have also multi-label classification. In multi-label classification, it's a classification task where each input sample can be assigned to multiple labels. So I have some object in an image, and those objects can be at the same time, can be labeled into two different classes, for example. So as an example, a given image may contain both a cat and a dog, and should be annotated both with the cat label and the dog label at the same time. So in this case, number of labels per image will be higher than number of objects, correct? So I have two objects, and those two objects could be classified into three labels, for example. So this is multi-class classification. And finally, we have regression, and it's a scalar. I mean, regression, we try to regress into a scalar number, for example, and it's a task where the target is a continuous scalar. So for example, I need to predict your income next year, for example. So it's a scalar, correct? So it's arranged. So if you are getting 100,000 euros, for example, per year, for example, so in this case, we need to predict your income next year as a continuous scalar. Or predicting house prices in Krakow, for example. So in this case, also the house prices will be a scalar, continuous scalar. If we need to for building a model, so there is something called universal workflow for model development. So first we need to define our problem if we need to use a classifier for solving a problem. So it's very important to define your problem first. What do you mean by defining your problem? Defining your problem means I need to see what kind of data sets which we have. For example, I need to see what kind of input features, what are my labels, how many classes. So first you need to define your problem. And after that, you need to collect the data for building a model for solving this problem. So next point will be data collection. After that, I need to choose a measure of success. If I need to build a model which will classify the collected data or which will be trained by the collected data, I need to select a measure of success. I need to measure maybe an evaluation metric or a loss function, for example. So I can see that I need to maximize accuracy, for example, or prediction. I need to minimize prediction error. So it's very important to select a measure of success. If you can measure it, you can control it. After that, if you want to train your model, before training your model, I need to select an evaluation protocol. So what will be my evaluation protocol? And based on this evaluation protocol, maybe I will split my data into a training set and a validation set, for example, and a test set. And you will train your model using the training data. And after that, you will use a test set for testing your data. So this evaluation protocol is very important. You need to decide your evaluation protocol before starting a model training. After that, you need to prepare your data, for example, data pre-processing, maybe feature extraction, feature selection, dimensionality reduction. So we can call it a data pre-processing, for example. So I need to do this on my data. I need to apply those techniques to my data. And after that, I will split my data for training and validation and testing, for example. And after that, I will train my model. And then when you are training your model, you need to start with a baseline model. It's very important to develop a baseline model. So you start with a simple model, and after that you test the accuracy of your model. If it is okay, so it's okay. Otherwise, you need to increase model complexity step by step until you reach the performance which will make you happy. So the next step after building your base model, you need to develop a better model. Try to fine-tune the hyperparameter of your model in order to enhance the model accuracy, for example. And at the end, you will validate your model, you will test your model, and you need to document your results and share it with different stakeholders. And after that, maybe you need to deploy your model, for example. So if your model will be used by different users using a mobile app, maybe it will be smart to deploy your model in a cloud, for example, or whatever. So, so at the end, we need to deploy our model so many people can start using our model. So you need to select a model, and this model will contains a number of parameters. It could be weights and bias, for example. I will use my training data for training my model, and after that, I will use a test set for predictions, testing my model, and update weights, bias, and document your results, and so on. Yeah. So how to define your model? So the following, you need to answer some of those following questions. What is the main objectives of my problem? What are we trying to predict, for example? So you need to answer those questions. If you need to predict something, if you need to classify something, so you need to define your problem very well. After that, you need to decide what my target features. This is very important. So what is my input data? Is it available? And if it's not available, how can we generate data? How can we generate more data? There are some techniques which can be used for generating more data from the small set of data which you have. And what kind of problems are we facing? For example, is it binary classifications? Is it clustering a problem? Is it regression? If is it binary or multi-class classification? So in this case, it's a supervised learning problem. So I need to select a model which can be used for doing this. If you don't have labels, for example, so it will be clustering problem. So in this case, I need to go for an unsupervised solution. It could be a regression problem, for example. Can my output be predicted given those inputs? So there are some statistical approach which can be used for, finding a correlation between inputs and outputs. So it's very important that you are collecting relevant data, because maybe for my problem, I will collect data which does not make any sense with my outputs, my labels. So it will be a problem. So in machine learning, they said that it's a rubbish in, rubbish out. So if you will collect irrelevant data, maybe your model will not be relevant also for solving your problem. So it's very important to collect data which makes sense with your problem at hand. Is the available data sufficient and sufficient informative to learn the relationship between inputs and outputs? Is it sufficient? Is it enough in terms of quantity and the quality? Right? So it's very important to answer those questions before building your model. In the data collection, it is the process of collecting and measuring information on target variables in an established system to enable one to answer questions and evaluate outcomes. So data collection is very important. It's very important to collect data which makes sense with your problem. Maybe you will collect your data from different types of sources, for example. Maybe if you have some sensors, so I will collect data from those sensors, correct? Maybe I will collect the data from customers by surveys, for example. Maybe I will do some interviews with some peoples, correct? For data collection, because interviews also, it's a data collection process. Maybe I will get data from books, magazines, images, and so on. So it's something very important we need to take care of. The more and the better data that we get, the better our model will perform. So it's a very, very important to collect as much data as you can and high quality data as you can. After data collection, data pre-processing, because maybe after collecting your data here, you need to visualize your data. You need to use some data pre-processing techniques. Maybe I need to select the most important features. Maybe I need to lower the dimension of your data using dimensionality reduction technique, for example. After that, you need to choose a measure of success or evaluation metrics. When we are building a model, I need to measure the success. I need to be sure that this model will fit my data. So I need to select a measure of success or evaluation metric. So there is very nice sentences. They said that if you cannot measure it, you cannot improve it. So if you cannot measure the success, if you cannot measure accuracy, for example, you cannot improve model accuracy. So it's very, very important to develop a cost function, for example, which we can use to measure the success of my model in classifying my data set. So there are some evaluation metrics which we can select, like precision, for example, precision, accuracy, recall, fairness, biasness. I need to build a fair model which is not biased. So you can try to select all those evaluation metrics and measure those metrics and use those metrics to compare between different models. Because maybe I will develop model A and I will develop another model which is model B, for example. But how can I compare between those different models? So we need to select some evaluation metrics which can be used to measure the maybe precision and accuracy of different models. And at the end, I will select the model which give me better accuracy. So I can calculate the accuracy of this model and the accuracy of this model, and I will select the model, or I will recommend the model which will give me better accuracy. So if it is a classification problem, so I can use those numbers. And also I can use something called the confusion matrix. This is very important. We can use some metrics such as F1 score, for example. It's very, very important. And if it is a regression problem, maybe I can use mean squared error, right? Because when it's a regression problem, I cannot use those precision, accuracy or something, but I can use maybe mean square error or mean absolute error, correct? So I can select some other evaluation metrics. So for classification problem, I can calculate precision, accuracy, and recall. But for regression problem, maybe we need to measure mean square error, mean absolute error, and so on. Evaluation protocol, it's very important. After collecting your data, after selecting evaluation metric, I need to be sure that my model is validated. So we need to select validation protocol. So maybe this one, it's not evaluation protocol, but it should be validation protocol. In fact, this one should be the validation protocol. What is my validation protocol? So this validation protocol, it is used to measure the progress towards achieving my goal. So there are some techniques. For example, there is something called hold-out validation, and one technique called k-fold cross validation, for example. So I can select one of those. If we need to validate our model using a data. So hold-out validation and the k-fold cross validation, it requires splitting my data into maybe 3 parts or portions or containers. So one for training, one for testing, and one for validation. The validation set, in fact, it's the test set for the training set. So if you want to build a model and validate your model, you need to select, of course, if I will go for hold-out validation requires having a large amount of data. If you have enough amount of data, I will split my data into one part for training, one part for validation, one part for testing. If you have less amount of data, we can go for k-fold cross validation. And in k-fold cross validation, we will split the data into k partitions or k-folds. And for each k, we will train the model using k-1 partitions and test it with k. And we will repeat this process k times. And each time we will calculate one accuracy. And at the end, we will calculate the average accuracy of my model. And at the end, we will train the model using the whole data set. So in this case, we will not sacrifice any data sets for validation or for testing. So there is k-fold cross validation. And we will go in details later on for those. So I just try to give you an overview of the things which we will cover. There is something called iterated k-fold cross validation with shuffling, for example. So we will use it when we have little data available. And we will apply k-fold cross validation several times and shuffling the data each time before splitting it into k-folds. So also I will go back into that later on with more details. So in classification problems, both the training and the testing data will be must be representative of the data. So I mean, when we are splitting our data into one part for training and one part for testing, we need to be sure that those data are representative of my data. We need to shuffle it before splitting. And we need to be sure that all classes are equally represented in the training and the testing sets. So it must be balanced. Otherwise, your model will be biased. So if you can remember here, we have biasness. For example, I can just give you an example. For example, in USA, for example, if you want to get a loan from the bank, maybe they will use some those criminal record, for example, and so on. There are lots of information they will use it to to decide if you should get a loan or not, for example. And usually those systems are biased against Black people in US. It's by default. So even if he is football player, he is actor, for example, he is extremely rich. When you go to get a loan, for example, the systems or those AI systems in US, they are biased against Black people. So they are assuming that Black people, they do more crimes, commit more crimes, or they should not get a loan, for example, from the bank, because those models, they have been trained using data sets which are biased. So when they try to build a system, those systems are built with unbalanced data sets. So those data sets, for example, assuming that Black people will commit more crimes compared to white people. So it's biased. The data set is biased. And when you train a model using a biased data set, I mean, the model itself will be biased. So it's very important when you try to build a model for classification problem or regression, whatever, you need to split the data into a training set and a test set. You need to be sure that all classes are equally represented in the training and testing. So if I need to hire people, for example, I need to build a system to select people, to hire people, for example, maybe in a sector like in oil and gas, for example, it's more dominated by men, correct? So maybe such systems will get each day maybe 200 CVs, for example, maybe 150 or 180 from male, and the rest will be from female. So in this case, females are not equally represented in those training and testing sets, for example. And if you will build a system to hire people, to select people for hiring in this sector, maybe those systems will be biased against women. It will not select women, it will select more men compared to more women. Why? Because the system is unbalanced, because I have more men compared to women, for example. So in this case, the system also will perform in the same way in the future. But if you want to build a system which is fair to everyone, for example, so in this case, I need to build a system which has the same number of white people and the same number of Black people, the same number of men and the same number of women, for example. So in this case, the system will perform more fair. If you are working with a time series, or with a text data, for example, in this case, we don't need to shuffle our data, because in fact, in time series, we try to use best values to predict future values. So if you will shuffle your data, you will destroy the context of your data, and it will not be possible to deal with the data as a time series. So whenever you are working with a time series, don't shuffle your data. You need also to check if there are duplicates and redundant data to avoid inaccurate learning. So, because if I have duplication in my data sets, for example, so I have an example which has been in the training and testing at the same time. So in this case, in fact, I will get better results because the model will be tested with a data which has been used for training it, for example, so it will be correctly classified. So in this case, I will get misleading accuracy from my model. It's just, but we will go back to it later on. This one, it's a hold-out validation, as you can see here. It's hold-out validation protocol. So this one we call it hold-out. In this hold-out, we split the data into two containers. One part for testing, maybe it's 80% will be used for testing, and 20% will be used for validation. So we will use that part for training your model, and we will use that part for testing your model. And as you can see here, I mean, the problem here, if you need to use hold-out validation, which is very fantastic technique, it's easy to use. I will shuffle the data and I will split at 80% for training, 20% for testing. The problem here is that the hold-out validation set will not be used for building my model, but it will just, we will keep it away for testing my model. So we need to sacrifice that part from the data. So we can do this if you have large amount of data. If you have very small amount of data, so in this case, we will go to this type, which is called the k-fold cross validation. So this one, we call it k-fold cross validation. This k-fold cross validation, we need to select k. K is hyperparameter. So for example, if you select k equals 3, so in this case, we will divide the data into 3 containers, 3 equal containers. And we will use 2 for training, 1 for validation, and we will repeat this process 3 times. So we will use this one for training, validation, and after that we will use those 2 for training and this one for validation. And at the end, we will use those two for training and this one for validation. And each time, we will calculate the validation score. So we will have validation score 1, validation score 2, validation score 3. And at the end, we will just take the average of those 3. So we will have an average validation score. This average validation score will be the average score of my model. And at the end, I will use the whole data for training a brand new model, right? Brand new model. So now I will train a model at the end using the whole data, using the three folds. And this model will have an average accuracy equals the average of those 3 accuracies, for example. So in this case, we didn't sacrifice any testing set or any validation set, similar to holdout validation. If you have any questions, please just ask. So just feel free to ask questions if we need to. But don't worry, I try to give you an overview. And after that, we will go into details and we will repeat this each week. So we will be sure that you will be able to do this by yourself and understand the concept very well and able to use a model for solving a problem. So after choosing the validation protocol and splitting your data, you need to select a model, or maybe first you need to do some data pre-preparation, for example, and the data pre-processing aims to make the raw data at hand more amenable to neural network, more suitable to your neural network model. So maybe you can use something called vectorization, for example. Vectorization, we try to convert the categorical data into a numerical value. We can use some normalization techniques. We can use, if we have some missing values, we need to handle those missing values. And also maybe you can use some feature extraction technique or feature generation, for example. We generate features, we extract features. We need to deal with missing data. For example, we need to eliminate features with many missing values. If you have lots of missing values, we can just eliminate those values, for example, without the risk of losing relevant information. Data imputation, we can use some data imputation techniques. If you have some missing values, we can replace those missing values with some estimates, such as the mean value of the rest of the samples. So, for example, you are collecting data and you have one column called age, and then maybe most of women customers, they will not report their age, for example. They don't prefer to do this. So maybe in this case, if the age, if we have too many missing values in the age column, we can just eliminate this column. If you have little, maybe in this case, we will just take the average age of participant, and we will use data imputation. So we will try to replace those missing values with the mean value of the age, for example, in that column. Data vectorization, we try to handle categorical data. We need to convert those categorical data into some integers, some numbers. So for example, if you have a data set and they will try to classify into dogs and cats, so maybe you can replace a dog with 1 and a cat with a 0, for example. So in this case, we will convert those categorical data with numerical values. And maybe after that, we will use one hot encoding to convert it into 2 columns, for example, right? To be much easier for my model to classify. Also feature scaling. So we need to learning algorithm perform much better when dealing with features that are on the same scale. Sometimes you have a regression problem, for example. One input is age, which is a number between maybe 20 and 60 years old, for example. And the other one is income, which might be 1 million NOK, for example. So in this case, I will have one feature on the scale from 0 to 1 million, and one feature which will be a number between 20 and 60, for example, because it's age. Maybe also I have another input, which is gender. So it could be 0 for male and 1 for female. So as you can, when you look into your problem, the input features, they have different scales, and it will make a problem to my model. So it's much better, in fact, to try to normalize. So all input features have are on the range between 0 and 1, for example. We can use min-max scaling. So if you want to use min-max scaling, so in this case, in fact, we will try to normalize all input features to have the same range, to be on the range from 0 to 1. So income will be a number between 0 and 1. Age will be a number between 0 and 1. And also gender will be a number between 0 and 1. It will be 0 for male and maybe 1 for female, for example, and so on. We can do also some standardization, which is centering the features at a mean of 0 and a standard deviation of 1, normal distribution. It's also something which might be useful. Those techniques are very easy to use, and if we will build our machine learning pipeline, it will be just one step. It will be one step or one phase in your data pipe in machine learning pipeline. So first, you will get the raw data. After getting the raw data, we can build a pipeline like this one. So we will have here raw data, and the output will be prediction, correct? Prediction. Maybe the first step here will be data normalization, and after that, standardization, model training, and prediction, for example. If you want to use a dimensional reduction, maybe also we'll have normalization and standardization, and after that, we will have a block for principal component analysis for dimensional reduction, and after that, model training, and after model training, we will have model testing, for example, or prediction, for example. So you can select a meaningful features. We can use principal component analysis to convert those raw data into principal components. Maybe there are some functions like select k-best, for example, it's feature selection. Maybe we can select this one. K here will be a hybrid parameter. You can say that if I have 4 inputs, I need to select the most important 2 features. Select 2 best features. So in this case, we will select k equal 2. So also we can use a technique such as this one. And this one is very useful because it will lower the dimension of your data. And then when you lower the dimension of your data, you will lower the model complexity. And when your model is not complex, chances to overfit will be much less. And in this case, you will need less data for training your model. And it will be easy to understand your model, in fact. You can use autoencoder, and autoencoder, it's unsupervised feed-forward neural network, which is used for lowering the dimension of your data. So this one will act similarly to principal component analysis. But principal component analysis, it's a statistical tool, but autoencoder, it's a feed-forward neural network. And after doing this, we will split the data into one part for training and one part for testing. And after that, you will train your model, test your model, validate your model, and after that, deploy your model. So this one, it's min-max scaling, and the min-max scaling, it's very simple. It's x minus x mean divided by range, which is x max minus x mean. So in fact, this min-max scaling, it's a very, very simple equation which we need to apply for each input feature. So x normalized, for example, it would be x minus x minimum divided by x max minus x minimum. Standardization also, it will be just a new feature. The new feature will be x minus mu divided by sigma. Mu, it's the mean. Sigma is a standard deviation. So in this case, it will be converted into a normal distribution with standard deviation with a mean equal 0 and a standard deviation equal 1. After data preparation, data pre-processing, you need to select a model. Imagine that you will select a feed-forward neural network or a multi-layer perceptron, for example. So you will use the training set for training your model, because we will split the data here, data splitting. We will split it one part for training, one part for testing. So it's a training set and testing set. So you will use the training set for training your model. So I will use X training and Y training for training your model. And the goal here is to achieve a model that can generalize or perform well on a never before seen data. So I need to select a base model. It's very important to start with a base model. Base model means it's the most simplest model which you can use, which can give you an accuracy higher than 50%, right? So I will use X-train, Y-train for training such a model. And after that, in the training process, we will try to adjust the weights or model parameters. And I will use the validation set as a test set for the training set to discover if my model is overfitting or not, because there is no way, in fact, for discovering that your model is overfitting during training process without using a validation set. So it's very important to have a validation set for testing, for checking your model if your model will overfit your data. From the validation error and accuracy, we can discover overfitting during the training and use techniques such as early stopping. There are some techniques which we can use, such as early stopping, to stop the training process so the model will not overfit my dataset. Because if the model will overfit, it will be very difficult It's a very critical situation when your model overfit your data, because you need to repeat the process one more time. So it's very important to use the validation error, and this validation error will be watching your model. So if the model will start to overfit, early stopping technique will stop the training process. Stopping the training process, which means I stopped the training process so I can have a model which has better generalization capacity. In testing, we measure the generalization power of your model to avoid overfitting and minimize generalize. And in fact, this one maximize generalization. This one should be maximize. We need to maximize generalization. Test set is used to evaluate the final model. After that, I will use a test set to evaluate the final model performance. A model overfit the data when it has high model capacity or little data. I mean, this is normal. Your model will fit your data if this model is too complex, or if you have a very small data set. So the model will consume it very quickly, and it will overfit. So it's very, very important to avoid overfitting by starting with a baseline model, and that is why we are starting with a baseline model, which is a simple model to avoid overfitting. And after that, if you got an accuracy which is maybe 55%, for example, now you know that this model works, and you can start increasing the model capacity by increasing the model complexity by adding more hidden layers, for example, more neurons in the existing hidden layers. So the model complexity, model capacity will increase, so you can enhance the performance of your models by 50%. Overfitting and underfitting, it's this one. I have a data set, and I need to fit a model into my data set, and I got this linear model. And as you can see here, this model is underfitting your data set, because if I need to predict this one, I will get a number here, not this one, but it will be like this one, which has very high prediction error. So this model, in fact, is underfitted by data set. This model, it's a good fit. I mean, this model, it's a good fit, right? It can predict those data points with very high accuracy. This model, in fact, it's overfitting. Why it's overfitting? Because the prediction error equals 0. So if you can look into each point, it was estimated very well, in fact. So the prediction error here, almost equal 0, because this model will overfit the training data, and it will perform very badly with a test set. How to discover it? Just from the validation set. So when you are training your model, you need to select a validation set, and you need to use early stopping technique, which will stop the model before overfitting. And if the model overfits anyway, so you will get error. The error for the training set will be almost very small. It will be close to 0, and the error for the test set will be very high. So the error for the test set will be very high number. So when the error for the training set is very small and the error for the test set is very large, it means your model overfits your data. So overfitting is very challenging. Underfitting is fine, no problem. But this one is very challenging, because now I need to reduce model complexity. But if you are underfitting, no problem. Now I need to just increase the model complexity a little bit to achieve better results. So it's much easier to go from this one to that one rather than going from this one to that one. Developing a model, at the end we need to develop a model which does better than the baseline model. Now I developed a baseline model. So if you have a baseline model which can give you like this. Yes?
I have a question. Because like in the schedule, we have like the lecture for 1.5 hours, and then we have labs for also 1.5 hours, like one group of us. So like, do we have those labs, or we just have to do like these 3 projects which you said about in the beginning?
No, we will have the labs, and in the labs we will have some examples. So for example, I will start after finishing those slides now. I just have 4 slides to finish.
Okay.
In the lab part, we will start with a perceptron, and we will take one simple example so people can start working and coding.
Okay, thank you.
Yeah, so that's just I try to give you an overview now. And in the lab section, after 15 minutes, we will start talking about a perceptron, and we will try to build the first simple perceptron in this lab. And during the whole semester, we need to have maybe 2 home assignments or 3 home assignments to write a report. So you need to have a problem and try to solve this problem using one of those techniques. and you need to write a report and submit this report to me during the whole semester. And those reports will be used for evaluating your grade, in fact. So you will get the grade based on the home assignments. So we need to agree if we need to have 3 home assignments or 2, for example, or 1 larger home assignment. So we need to discuss this. Yes, so I will just try to finish that part. So as I told you, it's much easier to start with baseline model and try to increase model complexity to achieve better results. So we need to go into that direction rather than going back from that direction, because it will be more complex if your model overfits your data, if you will be able to discover it. So there are some techniques which can be used to improve the model and to avoid improve generalization, for example, and avoid overfitting, such as early stopping technique. We need to use early stopping. We need to reduce model size, model size reduction to reduce model capacity. So, for example, if your model is very large, you can drop out some layers, for example, because we need to reduce model capacity. There is a technique called dropout. We use it also during the training process to avoid overfitting. And also there is some regularization techniques such as L1 and L2 regularization techniques. And those L1 and L2 techniques, it try to add some constraints on the values, which is a weight will modified. So we try to reduce the weight adjustment. So we try to put some pressure on the weights. So the model will not have too much freedom to adjust the weights, so we can avoid overfitting. So after getting your baseline model, you try to develop a better model than the baseline model by maybe selecting different try to develop this base model a little bit to enhance the model performance. We just need to fine-tune this model, the baseline model, maybe by increasing the model complexity or model capacity, by adding maybe more hidden layers, maybe adding more neurons to each hidden layer, for example, maybe try to test the different types of activation functions and so on. So this is the last slide. It's about feature engineering, for example. So if you try to build a perceptron, if you need to solve a problem, if you have a problem, and this problem you have the input is raw pixel grid. I mean, if you have this one as an input to your model, for example, and the output, I need to estimate the approximate time from this image. So I need to build a model where the input will be this pixel grid, and the output will be approximate time. So in this case, I need to build a model. You can go for CNN model, convolutional neural network. The input will be a raw data, and the output will be time. So in this case, I will select this one as a CNN model. Maybe if you want to use feed-forward neural network, I can replace this one with a feed-forward neural network, and I can work with raw data also pixel grid, but pixel grid in this case it will be pixel values. So in this case, the feed-forward neural network, it will be very complex, because if this one is, imagine this one, it's 28 pixels times 28 pixels. So in this case, number of inputs to my feed-forward neural network, it will be 874 inputs. So in this case, this model will be very complex. And if I don't have enough data set for training such model, this model will overfit. To avoid this, maybe we can work with this image a little bit and try to extract some features. Those features, it could be the coordinates of those handles. So I need to get X1 and Y1 for the seconds and for the hours handles, for example. And in this case, I will build a simple model with 4 inputs instead of 874 pixel values. Maybe also you can try to get simple formula, which is white box model. And in this case, if you can try to extract θ1 and θ2, the angles from those images, maybe in this case, I can just build a very simple formula, which can try to estimate the hours or the time based on those values. At the end, the place of feature engineering in the machine learning workflow, this is my workflow. We collect data from sources, different types of sources. So at the end here, we will collect some raw data, and I need to use those data for training a model. But between the model and the raw data, maybe we can have a block called feature extraction or feature engineering, for example. So we need to clean the data, we need to transform the data, we need to use standardization, normalization, and standardization techniques, for example, maybe dimensionality reduction, feature extraction, and so on. And at the end, we will get a set low dimensional set of features, and we will use those low set of dimensions, or low dimensional set of features for training my model. And this model should be used for classifying or regression or whatever. So anyway, the idea here is that you have a model, you need to build a model, you have a data collected from different sources. So you need to work with the feature engineering in the middle here between the raw data and the model part. So now this is all. It's just a general introduction about what we will do during the whole semester. I mean, those slides, it's like big umbrella, but we will go into details during each week. So for example, we will try to start today understanding what is a perceptron. We will try to build the first perceptron for solving a problem. And each week we will go through those concepts and we will repeat this with time also. So we will be sure we will not finish a topic before you have good grip of it, you have good understanding of those concepts, and before you are able also to try to build a model and use those techniques for solving some problems. So thank you very much for listening to those slides. We will take a break now, and we will start again at 11, maybe 11:20, for example. So please, if you have any questions, we will take those questions in the lab section, and we will start the lab section after 15 minutes. Thank you.
Thank you.
Thank you.